So we're getting close to being finished with this chapter, but there are some other types of logarithms that we're going to talk about. This one specifically is called natural logarithms. The question is, what are natural logarithms? So far, we've just been calling them logarithms, but now we're calling them natural logarithms. What are they? So we're just going to jump right into it to see what it is. Natural logarithms. So they're logarithms, just like any other logarithm, except for the base. This is pretty important here. The base here is e. Now, if you recall what e is, remember e is just a number. E stands for 2.7128 ... right? So one way it's written is to write it out as log base e of x. That's all it is. But instead of writing this as log base e all the time, they replace it with something new, which is going to be called a natural logarithm. They use the letters ln. So instead of writing log with a base at all, it's written as ln. So this would be ln of x, same thing as log base e of x. So these are interchangeable. You can go back and forth between the two. So you should now recognize what this means. There's also a button on the TI-84 calculator that is ln. So you can just hit that button and type in whatever number comes next. All right, definition of natural logarithms. So n is a natural logarithm of m, which how you would write like that is this. How you'd write it, it would be, n is a natural logarithm of m. So we put ln of m equals n. So we're going to practice changing this into exponential form. This is only true if, which maybe I should actually do this. If you remember, like these are the same thing, right? These two are the same. I could rewrite this as log base e of m equals n. And then you can kind of just do the circle thing, right? How do you change this from a log to an exponential? You would start with the base e, go around to the n equals m. And so that's only true, ln of m equals n, if you can write it this way. E to the n equals m, right? Get rid of the log, and then just rewrite it. So we're going to practice solving some of these equations where we're going to have x in the middle here, but then as you go around the circle, you'll see x will end up being by itself on this side. So let's try an example. Convert the natural logarithm equation into exponential form in order to find x. So we're going to do ln of x equals 4. Now what I'm going to do is I'm going to replace it with writing it like this. That way it's easier to figure out how to solve it. We can do log base e of x equals 4. Now I'm going to change it to exponential form. So this is where we get rid of log. We start with our base e. So we do e to the 4th power equals x. And you can type that into your calculator if you have one. You can also always use Desmos, which I will use. So I'm going to do e to the 4th power. It's going to be a decimal. 54.598. 54.598. There you go. All right, we'll try another one. ln of x here. I think eventually you don't have to keep writing it out as log base e, but for now I'm just going to write it out one more time. Log base e of x equals 0.5. Right, these mean the same thing. And then to change this to exponential form, we would get rid of the log, start with our base e, go around the circle, e to the 0.5 equals x. Put that into the calculator and we'll be done with this one. E to the 0.5. So just change this to 0.5. 1.648. There you go. Okay, last one. And maybe we can try doing this without changing it to logarithms. So if you just realize that ln of x is the same thing as having a base e with a log, you can probably just put a little e there and then go around the circle. So we're going to take out the ln, go around. It's e to the 1st equals x. back around here. And e to the first is just the number we know, 2.7128, ... right? And then so that's how you change it from exponential or from logs to exponential form and solving these for x. Now, example 2, estimate the following to the nearest thousandth using a calculator. So you can use Desmos, obviously, for this one, and then you can also use the calculator at school. There is an ln button on the calculator, which is capital Ln. I think it's right around where the log button is on the left, right below it, I think. So let's try these. Do ln of 100, ln, whoops, hopefully that works on here, ln 100, and that is 4.605. ln of 5, just practice doing this in the calculator. ln of 5, 1.609. Did we see that already? 1.648. 1.609. And last one, ln of a fourth. 1/4. Oh, no, not that. I have to put in parentheses. 1/4. There we go. Negative 1.386. Okay. And then that's how you do them. You can type them in Desmos. You just type in ln and then the number. This particular case in part C, I had to put in parentheses to see the 1/4. Or you could have used 0.25. I guess it didn't really matter. Let's delete this. 0.25. Still negative 1.386. All right, how about a graph of this? Now, we haven't done any graphing with logs yet. So I'm actually going to jump down and graph this, part F. I'm going to jump down to part F. It says graph y equals e to the x on the same graph above. We'll compare their shape. So let's do e to the x, because we know it's the same thing here whenever you kind of change this to exponential form. Let's graph y equals e to the x. E to the x. All right, there we go. And you could also bring up a table if you wanted to see some values. So 0.1, 0.36, 1, 2.7, 7.8. All right, I'll try my best with that. So negative 2 is 0.1, 0.3. 0 is 1. 2, or 1 is 2.7. And 2 is 7.3, right? Or 7.8. 7.38. So there. Okay. So this is our e to the x. And then I'll probably just change colors to the other one. And if you remember, this e to the x and ln x, they're kind of like opposites of each other. Like we said before, when you have exponential form and logarithmic form, they're like inverses of each other. So think about what the inverse of this would be. Right? What kind of shape would that be? We're going to put it into Desmos, and you'll see exactly what it looks like. We're going to graph from 0 to 1, 2, 3, 4. Put some negatives on there too, maybe. Let's see. So I'm going to keep the table up here. Let's make a new equation. We're going to do y equals ln x, and we'll see what it looks like. So there it is. I'm going to also throw in one more. We'll do y equals just x to show you how they're inverses. See how it cuts it right in half there? And I'll go ahead and pull up a table on the ln x. So the reason why we didn't do any negatives here is because they're actually undefined. Let's throw some more numbers on here. I'm going to have to keep going, enter a couple times. All right. So we'll try our best to plot these. 1 is 0. So I'll change colors here. At 1, it's 0. 0 is undefined. Maybe I should put it on here first. Undefined. 1 is 0. 2 is 0.69. Then we have 3, 1.09, and 1.38. 09, 1.38. All right. So 2 is 0.69, not that high. 3 is 1.09, barely over 1, and 4 is a little bit above that. And we do have numbers, as you can see, this is kind of like slanting down, but it's not going to cross this. Looks like we have another asymptote, right? If you zoom in, it doesn't get touching the y-axis. It gets closer and closer. And then we have this kind of just veering off this way. It's not really growing that fast. It takes a while to grow. So we kind of have this thing like sloping up like this. I'm not going to draw it the best. It's hard to draw on this thing. And then kind of down like that. And then if you do y equals x and cut this halfway through, you should see that they are inverses. So my red one is y equals ln x. Okay, domain. If you remember the domain and range of e to the x, or any exponential ones we have, this is going to kind of just be the opposite. Domain is all the x values. So we're looking at the red one now. If you notice, the x value that it does not touch is at 0. It does not touch 0. And it's never in any of the negative values. So we're going to say it comes down and gets closer and closer to 0, but doesn't touch it. So it's going to go from 0 to infinity, which was the range of exponential forms that we had before, exponential functions. And then the range, well, it goes down forever and also goes up forever because it keeps getting bigger and bigger. It's just growing ever so slightly, right? If you kept going, it would get bigger and bigger and bigger eventually. Just not that fast. So it's going from negative infinity to positive infinity, or you could use that, either one. X-intercept, this one does have an x-intercept. It's right there. It crosses at 1. Y-intercept, it does not touch the x-axis, so there's none. And the asymptote, we just talked about this. This gets closer and closer to the y-axis, but never touches. So everything is just kind of opposite from what it was before when we did exponential functions. It's the opposite of this graph, e to the x. I also want to show you some other ones on here, because I know we're going to get to a word problem now. Is that all then? Just one word problem? Yeah. So let me show you another one on Desmos quick. Back these out here. So you could do other ones. Let's do another log one. Y equals log. And if you wanted to get a base on this, you have to hold a shift, and right beside the 0 is like a dash. Puts it underneath like that. There might be a log button on here. I've never used it before though. Functions. Here's ln and log right here. You can probably use that button, or log base a. Okay. Anyway, you could just hold underscore, a shift beside the 0. Let's just do log base 3 of x. Look at this. So there's another one like that. It's just not e to the x. And then the inverse of that would be changing this around. This would be 3 to the y equals x. In other words, 3 to the x. And there you go. You have another set of inverses. So these kind of are the opposite of each other. One grows really, really fast, exponential. This one grows really, really slow on the opposite end. Okay, let's try a word problem. This one is pretty involved, but this will be like the only big word problem I think we're going to do. And then it'll be huddle to do the rest. Let O sub 1 and O sub 2 be the temperatures of a cooling object before and after taking T minutes to cool. There's a lot of stuff going on here. So temperature of a cooling object before and after taking T minutes to cool. Let S sub 1 and S sub 2 be the temperatures of the surrounding environment before and after those T minutes. It's kind of confusing, I know. We'll talk about it, though. Newton's law of cooling says that T varies directly as a natural log of the ratio of the differences in temperature between the object and the surrounding area. That's all pretty confusing, but it's just leading up to this equation. T equals K times ln, in parentheses, you've got this big fraction, O sub 2 minus S sub 2 over O sub 1 minus S sub 1. Okay? The constant of variation K depends on the temperature scale, Celsius or Fahrenheit, the type of the container the object is in, your altitude, and other environmental conditions. So this K value changes depending on kind of where you are and what you're trying to get cold over time, right? We're going to be talking about some food, some soup specifically, it being cold over time in a specific container. So these things will change how fast something cools down. So here's a question. After bringing it to a boil, which is 212 degrees Fahrenheit, Laura let her soup cool for 15 minutes to 140 degrees Fahrenheit. Use the data to find the value of K if Laura is making her soup in an 80 degree Fahrenheit kitchen. There's a lot of stuff going on here. So we're trying to find K. We don't know K. That's going to stay the same. What do we know? How long are we letting the soup cool? Cool for 15 minutes? I think that's up here as T, right? Before and after taking T minutes to cool. So we're going to use this as T. What else do we have? So we're bringing it to a boil. So what do we have that up here? This says O1 and O2 be the temperatures of a cooling object before and after taking T minutes to cool. Okay, so this would be the before one, that's O1. And after we let it cool, we get down to O2. And we have one number left. She's making her soup in an 80 degree Fahrenheit kitchen, but we have two variables. We have S1 and S2. That's the temperatures of the surrounding environment before and after you let it cool. And we'll say the surrounding environment doesn't change. We'll keep it an 80 degree Fahrenheit kitchen. So this is going to be both S1 and S2. Because before and after, we assume the temperature in the kitchen has not changed. Okay, I think we're ready to set it up now. So we have T, which is 15, equals K, we don't know, times ln. Big thing. What's O2? That was 140. Minus S sub 2, which we know is 80. All over. What did it start at? 212 minus 80 as well. So our goal is to solve for K. Alrighty, it's not going to be too bad. So I'm going to keep this 15 equals K times. We can do this part in the calculator. I'm just going to simplify a little bit further. Whoops. We'll do ln 140 minus 80. Right, that's 60. 212 minus 80. What would that be? 132? I could divide them now. Do I want to do that? Maybe. It'll give us a decimal of 0.45 repeating. So I'm just going to put this part into my Desmos to see what number this is, and we'll probably have to round it to some point. So let's get rid of these ones. We'll do, what was it, ln of parentheses 60 over 30, 132. Okay, negative 0.7884 is what I'll use. K times negative 0.7884 equals 15. So we have multiplication here. I'm just going to divide by this. I hope I typed it in right. ln 60, yeah, 132. Divide by negative 0.7884. Let's see what we get. 15 divided by negative 0.7884. I got about 19. Negative 19. And it's 0.02, so I'm going to just keep it like that, negative 19. So that would be our K value. Okay, that's our K value. Suppose Laura heats a pot of vegetable soup to boiling and lets it cool 15 minutes before serving. Is that what we had last time? Yep. What is the serving temperature of the soup if the kitchen is 70 degrees Fahrenheit? So we have a couple things changing, I think. Lower heats a pot of vegetable soup to boiling. So we're starting at boiling temperature. That doesn't change. Still 212. That's a cool 15 minutes. That doesn't change, does it? Still 15. That's T. This is going to be our starting temperature, I think, which was 212, right? Beforehand. What was that variable? S2 or S1? Oh, no. O1. Whoops. All right. What is the serving temperature of the soup? Kitchen degree is the surrounding one. That's your S1 and S2. We don't know the temperature it's going to be afterwards, so we don't know O2. That's what we don't know. Everything else we do know. We also know our K value because that's from before. We're assuming we're in the same environment, the same area. Okay. So we should have 15 minutes equals negative 19. That's our K. Times ln. Let's go back here. I don't know O2, so I don't know O2 minus 70, surrounding, over O1, 212 minus 70. Alrighty. I'm going to go ahead and probably just simplify this a little further. ln, we have O2 minus 70 over, that would be 142. Okay, not much I can simplify there. So we have multiplication between these two things, and since I can't really do this part in the calculator because it's O2, I'm going to divide both sides by negative 19. So 15 divided by negative 19, 0.789, negative 0.789, equals ln of this mess. And then, well, how in the world do I unpack all this stuff? Well, we have to figure out how to get rid of ln. And if you remember, that's the same thing as log base e. So I'm going to write this out again as another step. It's 142. So how do we get rid of that? We're going to go around the circle, but now we're going to go backwards. E is our base. To get rid of log, go e to the exponent equals that mess here. So something that's kind of tough. We're going to go e to the negative 0.784 equals, this goes away, the O2 minus 70 all over 142. Let's figure out what e to the negative 0.784 is. .4565. 0.4565 equals O2 minus 70 over 142. Then we're just going to solve this for O2. Get rid of this fraction. I'm going to multiply by 142. On this side, same thing. 142. And I'll put that in here, I guess. 142 times 0.4565. 64.83 equals O2 minus 70, because these 142s will cancel. And then I'm just going to add the 70 over, which would be 133.83 equals O2. Right? 134. 134. This one was pretty involved. So this would be, what are we looking at? Let's go back and look and see. What is the serving temperature of the soup? If it's in a 70-degree oven, it would be 134 degrees Fahrenheit. So we started at 212 as our boiling temperature. And over the 15 minutes, if it's a little bit cooler, we got down to 134. What was it before? Oh, okay. Before we waited 15 minutes in an 80-degree kitchen, and it dropped to 140. So if it's a little bit colder of an environment in the kitchen, in this case it was 70 degrees, it should be a little bit cooler of soup. We waited the same amount of time in the same area. It was just a little cooler. And we started with the same temperature, right? 212 degrees as a boiling temperature. And then it dropped down to 134. So it's a little bit less than if we had an 80-degree kitchen compared to 140. This is also in degrees Fahrenheit, which I can add to. There. The rest of it is for you to try. You're going to do another word problem, although it's not nearly as involved. It's a lot easier, I believe. This one was quite a lot. It's kind of really ramping it up. And then you'll finish off the huddle and the mastery. This one here is a challenge problem, so if you can't quite get it, that's okay. But the rest of it you should be able to finish. And that's all for 9.8.